All right, so this is the equation for the current, right? We say this is how the current decays, yeah, when we're discharging a capacitor. Now, let's just say, for whatever reason, that we wanted to get an equation for the voltage, right? The voltage drop. Well, this is awesome. Remember, V equals IR, right? So here we have I, so how can I get a voltage? Just multiply by R. Yeah? Right? So this is just the voltage as a function of time. This is the initial voltage times e to the minus t over tau. Ta-da! Nice and simple, huh? So that works out really well, doesn't it? So the voltage and the current have the same mathematical shape, you know. They're all e to the minus t over tau. All right, so that's nice. Okay. You have to know your algebra to do these kinds of things. So here's some practice for you. The current in a discharging RC circuit varies with time according to I equals I0 e to the minus t over tau. What is the discharge time t? So basically what I'm asking you to do is solve for t. So this is a math question. So pause your video and figure it out. And make sure you know how to do this because you're going to be doing this in your homework and your exams. Okay, I'll show you how to do it. Oops. What? Okay, let's do it. All right, so this is kind of similar to one of those math problems you had on your math test, right? That you took before the semester, at the beginning of the semester. Okay, so you're trying to solve for t. Oh, man. All right, you're trying to solve for t. Okay. So, first thing, and you can do this however you want. This is the way I do it. So first thing, get rid of the I0. So you have I over I0 equals e to the minus t over tau. Okay, we've got to get that. It's in an exponent. We've got to get it downstairs. But it's an e. How do you get an exponent downstairs with an e? You take the natural log. So take the natural log of this side, and you take the natural log of that side, right? If you do something to one side of an equation, you've got to do the same thing to the other side of the equation. Okay, so hopefully you remember the ln and e are inverse functions. They undo each other. So ln of this is just minus t over tau. All right? So here, let me just rewrite it. So we have minus t over tau equals ln I over I0. Okay, we're trying to solve for t. So multiply both sides by the tau. Let's do two things at once, huh? Let's multiply both things by a negative. So negative, negative is positive, then we have negative. Then multiply by tau. So you have t equals minus tau ln I over I0. So, which is the correct one? Let's see. Where is it? Oh, and one more thing. I guess I was being... All right. This is correct, but we're not done yet. So now you got to remember your log rules. A ln b is the same thing as ln b to the a power, right? You better know that. Okay, that's just good old high school algebra, you know? So we have a negative here, right? Can't we put that, this is like a -1. So can't we put that negative up here? Yeah, we sure can. And then what is something to the -1 power? You just flip it. So that's the same thing as tau ln I0 over I. So it's number 2, right? Number 2. Now, you didn't have to do that last step. You could have left the negative in there. Okay, I'm just trying to be, I don't know what. Okay, now, one thing though, look at, this is completely ridiculous. This is ridiculous, that's ridiculous, that's ridiculous. These four are totally impossible because, the argument of a natural log has to have no units. Well, this is time, this is current. That has units, right? All of these have units, so these four are completely impossible. These are the only two that are possible, okay? So anyway, make sure you know how to do this because you're going to be doing it. So make sure you know how to do it. Just good old algebra. All right, so that was the discharging capacitor. Now we want to talk about a charging capacitor. Okay, so here we have so there's a battery, the switch is open, here's the capacitor, okay? So, and we're going to say that the capacitor initially is uncharged. All right, so with the switch open, there's no current, right? There's no current, and so nothing is going on. But if we close the switch, then we're going to have a current that flows, right? In this direction, okay? So there's going to be a current that flows. So what we want to know is how does the current depend on time? That's what we want to know. Okay, now, let's see. So we're going to fill this up with positives, and we're going to fill this up with negatives. Now initially it's uncharged, right? So it's going to be it's going to be easy to fill this thing up with positives initially. But as time progresses, there's going to be more and more positives, so there's going to be more and more repulsion, so the current's going to get smaller and smaller and smaller. Okay? It's going to get smaller and smaller and smaller. All right? So what do you think it's going to look like? Well, guess what? So initially, the magnitude of the current is really, really big. But then it's going to get smaller and smaller and smaller as we jam those positives on the same plate, as we jam those negatives on the same plate. So I'm not going to derive it because it requires calculus, but that's the equation again. Have you seen it before? Yeah, you sure have, right? Okay. And so same thing, right? The tau is the RC. All right, and, I didn't see that. Okay, now, the voltage equation is not as simple as, you can't just multiply by R like we did last time, all right? Sorry, you just can't, okay? But let's think about it. Let's see if we can sort of just argue or philosophize, all right? Let's see if we can philosophize and try to figure it out. So Q equals C delta V, no kidding. And so therefore, delta V equals Q over C, right? All right, now, so in other words, the delta V is proportional to the Q. No kidding, right? No kidding. All right, so what's the initial voltage? 0, right? Because it's uncharged, agree? So the initial voltage is 0. And then what happens? Okay, look at the picture. Okay, so initially we have an uncharged capacitor. Then we close the switch. And then we keep getting more and more positives, more and more negatives. So initially the voltage is 0. Then as we keep getting more and more charge, as the charge keeps getting bigger and bigger and bigger, the voltage gets bigger and bigger and bigger, right? So it starts out as 0, then it gets bigger, 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 bigger. But eventually, this is going to be fully charged, right? It's going to be fully charged, and therefore the voltage is not going to change anymore. Okay? So it's going to start out 0. It's going to start out at 0. So it's the voltage versus the time. It's going to start out 0, get bigger, 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 and then it's just going to level off. It's going to be the same. Now, what is that? Well, sorry, but this is another one of these equations that you're going to see all the time in physics and in other sciences. So this you know, that's the e to the minus t kind of thing. This is the 1 minus e to the minus t kind of thing, right? So here it is. The voltage as a function of time equals the maximum voltage times 1 minus e to the minus t over tau. So you better know these equations. You just see them a lot, right? E to the minus t, 1 minus e to the minus t. You just got to know those. You see them a lot in physics and in other sciences. Okay, and just for fun, I just played around with Excel. So if RC is 1 second, you know, look at RC is 1 second, bang! It doesn't, you know, it's really fast, right? It doesn't take very long at all to reach the maximum voltage. If RC is 10 seconds, it takes a little bit slower to get there. If RC is 100 seconds, you know, it's going to take a while, right? So anyway, so we can just see that the curve really depends on that tau, the RC. All right, that's a long chapter. We're not quite done yet, though. Okay, so what did we do? We drew and we interpreted circuit diagrams. We analyzed circuits with resistors in series and parallel, Kirchhoff laws, and we analyzed circuits, and we talked about RC circuits. Okay, now, here are the equations. Just like last chapter, just lots and lots of equations, you know. This is old hat, we learned that, right? Conservation of current, all right? That's the Kirchhoff junction rule, Kirchhoff loop rule. Okay, adding resistors in series, same current, you just add them. If they're parallel, they have the same voltage, it's that crazy 1 over R rule. Then capacitors is completely opposite, right? So series has the same charge, and it's the 1 over rule. Parallel, same voltage, no kidding, but now you add them, right? So, you know, right? RC circuit discharging, RC circuit charging. All right. Okay, now,